understand the reason. Okay, it should be fine now. Let me also put it closer to the sound source. Thank you. Good. So you have this work of wisdom, and now we kind of express it in more mathematical and practical terms. First of all, let us discuss general states of a photon field. And I would like to arrange at the moment arbitrary superpositions of these states. What is the idea behind this? Well, first of all, any quantum system which can be in a set of basis states can also be brought to a superposition of the states. So any linear superposition of quantum vectors is allowed, right? So that's what I attempted to do, kind of arbitrary function of a wave function of a photon field. Right, here I have basis vectors of the field. We remember that they are given by occupation numbers of all k, of all alpha, so it's already infinite. One set of these numbers, and each state enters to this state with a coefficient, with an amplitude of superposition. Okay, if we know that if we assume that the state is obeyed by simple usual Hamiltonian for non-interacting photons, then we also know how does this amplitude depend on time. Let us see. Guess I missed stage bar here. No, I didn't. No, I did not. Who can tell me what does this expression correspond to?
Is it the energies in the harmonic oscillator?
It is an energy, that's right. It has something to do with harmonic oscillator, but with oscillators rather than with a single one. So we see the field as a set of oscillators. Each mode is an oscillator with index k and alpha. Each mode has occupation number, and indeed this quantity is proportional to the energy of a certain state of the field. Yes. Oh, I didn't have T. Oh, sorry. T. Of course, T. Your question?
Same question.
All right. Same question. Right, so just time dependence of a function is defined as Hamiltonian, and basis states are eigenfunctions of the Hamiltonian. That's why the time dependence is simple. Good, so it's a superposition we will look at, but again we will look at very certain superposition which we will call coherence. So let us first discuss the time. where we are going to achieve this one. And that's pretty simple now. I've taken an electric oscillator, I could take any oscillator, but let me concentrate on electric oscillator, which has a voltage source. And in the beginning, oscillator is whatever, classical mechanics without charge and current. Quantum mechanically, it is in a ground state. Good. Let us make a pulse. Let us give a pulse of voltage to this oscillator. Okay, classically, we understand pretty well what is going on. Those are equations for the oscillator, for charge at the plates of the capacitor, for current in the inductor. And upon applying a pulse, current and voltage, which is same as charge, would increase first. Pulse is finished, but we have already excited an oscillator, right? And there is no dissipation. So after that, the oscillator will oscillate in principle forever. Fine. Again, we see a little bit of controversy. If we really believe that gear exists only in big oceans, we have a difficulty here because it would imply that amplitude of these oscillations would be quantized. So when we tune the pulse, we would have a difficulty to change the energy of these oscillations. So we need to understand it better, and for this, we could take as a guideline our classical approach and make it quantum mechanical. I'll do it in a way we did already the quantization of the bands. So there was some work at classical level to introduce convenient coordinates suitable for each oscillator. Right. For oscillator in hand, convenient coordinate is like this. Okay, it's imaginary, it contains ugly square roots, but after you kind of accept this, the resulting equation for this variable will be very good. So this is without pulse, and it just means that d is proportional to exponent I omega t oscillations. So if I plot imaginary and real part of d, each oscillation will be circular. Fine. And the voltage just comes in this combination. Right, so we understand what happens with D when we apply pulse. Again, at classical level, first it was at 0, then during the pulse, it evolves to some level, then it will just stay at this level, rotating like this. Fine, convenient coordinates. Now we will consider it at quantum level. There are many ways to do this, according to simplicity of the problem. I could say, for instance, solve Schrödinger get equation for this oscillator, we do it with a bit trick. Let us see. First of all, we quantize this, and then we express voltage and current as we did when we quantized the oscillator in lecture number, I believe it was 7, right? We just put rewrite it in terms of creation annihilation operators. That's what we have without voltage source. Voltage source, in fact, brings terms of the first order. Okay, intuitively one understands their significance. These terms create and annihilate photons, so voltage can accelerate or decelerate the oscillator. Fine. Let us now get to Heisenberg picture. So we don't care about wave function. We look at time-dependent equations for this relation and relation operators. Okay, we do the algebra of commutation. That's what we obtain. It looks like an equation for D, except unknown this equation became an operator. Good. Then we have a problem which we got yet at school banks. It's a linear equation with a source. Then we have either the sum of the solutions. One is a solution of original equation. And this is pretty standard creation annihilation operator. Plus, we have an effect of the source. And that appears to be just classical solution for oscillator equation. It describes rise during the pulse and some finite amplitude thereafter. Good. So, to distinguish it from Schrödinger equation, it appears to be a very easy problem if you do it in Heisenberg picture. That's one of the reasons we have studied Heisenberg picture from very beginning. Yes, the question.
I was wondering where the d is a function of t in this case comes from. Is that the same?
Yeah, it is same as in this transparency solution of this equation. So classical, a solution of classical equations in convenient coordinates. So again, so as a result of voltage source, this relation operator just got an addition, constant addition. Fine. Now let us see. We are, in principle, we are happy, but we still do want. It was in the title of this lecture. I could not stop here. I have to produce a state, quantum state, right? So I need to make yet another trick to understand what is the state. Let us see if I still remember this. First of all, correspondence. Since the operators got this shift that, in Heisenberg picture, state did not change. So it remains vacuum. Or I don't understand what has happened. Hopefully, I'm still online. Perhaps there is a problem with Zoom. Can you see it now, Daniel? All right, perfect. Perhaps Zoom was overloaded. Right, so this is a correspondence between Heisenberg and Schrödinger picture. We want to use it to figure out which is the state psi. We can generalize it to arbitrary functions of the separators. It should give the same. Right, but for an arbitrary state, for an arbitrary function, there is such a correspondence between Heisenberg operator and Schrödinger operator. They just differ by addition. So this just an arbitrary function of this d of t. Right. So we can rewrite this as follows. How to solve it? We have an operator and we have the expectation value of this operator. And we have it at arbitrary functions of this operator. The only way it can be satisfied is that this wave function is eigenfunction of this operator. Eigenfunction of operator B with this eigenvalue. Fine. So we understood that the resulting state is an eigenfunction of annihilation operator. Right. Now we can use it to this equation to do math and to understand what does this mean. This is definition of coherent state so far. All right. It follows already from this definition that no way this function is a number state. It must be a superposition of different numbers. Yes, question.
Could you perhaps explain where the last step in the sentence from concrete form follows?
This. This. It follows from what we obtained here. Okay. Plus, we have used the fact that if annihilation operator works at vacuum, it gives you zero. That's why the last equality sign should hold. Fine. It is not occasional that I'm talking now about arbitrary function f of this operator. If it was just first power of b, it wouldn't differentiate. But it's the same equation for second power, third power, fourth power, and so on. So if it is valid for all powers, the only way to satisfy this equation, if this wave function is an eigenfunction, is this eigenvalue. Good. So once we understood this, we can look at this wave function in a form of superposition of different number states. We need to recall ugly square roots coming from definition of an annihilation operator. Square root of n, square root n plus 1. I always forget. Have to think to write it correctly. So with this we have an equation which relates subsequent amplitudes in the time. That is solution was a trivial. We have initial amplitude psi 0, and we multiply it at each step with this number. We can express it in general, so products of these things are just collected in square roots of factorials. Psi naught cannot be defined from this scheme, but we can get it easily by binarization. So anyway, all quantum equations are linear. They would define your wave function upon a common factor. This common factor, at any rate, has to be defined by normalization. Right. Normalization also works here because we can sum up this row, this sequence, just expansion of exponent. Fine. So this is explicit form of a coherent photon state. Lambda is a parameter. Lambda is generally complex number. The eigenvalue doesn't have to be real. It would have been so if the operator is Hermitian. No, he is not Hermitian operator. It can be arbitrary complex number. Right, let us see, let's make some visualization of this coherent state. First of all, I'd like to compute the average number of photons in the state. That's also simple algebra. We can do it explicitly, summing up this row. So lambda squared is average number of photons. So one could express lambda as square root of average number of particles, and some phase vector. To describe without remaining oscillations, and oscillation lambda eventually has to be time dependent. It has to oscillate with the frequency of this oscillator. So, in fact, it is an all bit. So, in order to have better visualization, let me do the following. We have plotted something in a complex plane of D. D and lambda are related on the scale of square root of h bar. So let me use the plane of lambda. And first of all, I would like to draw not the coherent state, but rather a number state. How would I draw? I would use this formula. Number of photons will give me lambda squared. So here I put the states with the same modulus lambda squared. So number states are circles in this plane. And coherent state is eventually such how can I put, let's say, such a disk. It's a disk of unique 104 radius. In this line, it's the best representation, visualization of coherent state. The center of this disk does depend on lambda. Lambda defines the center of this disk. What is perhaps interesting to know now, if the center is sufficiently far from the origin, it overlaps with a big number of number states. So there are still many number states in a coherent state with big lambda. Interesting. Let us try to quantify it. Let us talk about distribution of number of and this is distribution which I perhaps too optimistically would believe you know. It's a Poisson distribution. That's actually the same which we have in lasers, but if you recall your previous situation here, I believe you can come up with some examples of Poisson distribution. It's a distribution of independent lines. Right? So it's a distribution which depends on the parameter, and this parameter can be made the average of this distribution. Average number of points in this case. And at big averages, the distribution can be approximated by normal Gaussian distribution, which is centered at a given average n and has a spread around it. which is also square of the spread is also proportional to n, and the spread is just the square root of n. So relative accuracy becomes smaller if n is increased, but absolute accuracy decreases. Okay, it might ring the bell if you think of accuracy of measurements and accuracy of independent measurements. If your measurement has some mistake, to improve accuracy, you have to, relative accuracy, you have to make many measurements. Good. That's properties of this coherent state. Let me compare the distribution of photons in Blackbody radiation and that in a coherent state. Okay, it's a Poissonian distribution, and you see that it is concentrated at a big average number of photons. This is a Blackbody given by this. It falls off exponentially. This picture is not made by me. I've got it from a paper. Let's again try multiple choice questions. This paper is written in who has A? Okay. You also A? Okay. Who has B? Okay. Who's C? C is correct answer. Look, if you are in trouble, you avoid these things, okay? That also doesn't have to work in our multiple choice questions, but it's a piece of general wisdom. Good, why it was 68. Could have been that year, that time people thought about Blackbody radiation. Well, however, they don't see that they didn't have any lasers. So there were no applications of coherent state. And lasers kind of came into practice around this year. Yes?
Did they even know about coherent? Did they even know about coherent states in 1912?
They did, to some extent. I also show you transparency with this. However, it won't not be instructive. It won't be practical to compare these two in the same plot. This is from a classical paper about lasing. And actually, we have derived it already. Distribution of number of photons in laser is Poissonian. Well, good. Yes, that's what I wanted to say, that coherent state is very old stuff. It was first introduced as a byproduct of heavy thoughts by, this old guy, Professor Schrödinger, about basics of quantum mechanics, that uncertainty principle didn't fit his mind. He wanted to understand it better. And he has an idea, why don't I understand which state provides minimum uncertainty in this relation, minimum uncertainty in momentum and coordinate. Or whatever he wanted to prove this relation, finds a lower bound. Okay, it's in principle a minimization problem. It has nothing to do with the oscillator. You don't use Hamiltonian of the oscillator. You just try to minimize this relation with respect to wave functions. This is what he has found. And this is a vacuum state of an oscillator, but it is not yet uniquely defined. You can shift this state both in momentum and coordinate. And the right, this vacuum upon the shift will become a coherent state. Does that make sense? If it's better to do it shifting in X position. We have an oscillator, ground state, and now we shift the oscillator instead of kicking it. So the state didn't change, but it would, the particle would go to higher in the oscillator, so it will oscillate, it will be excited state, but it will be still coherent. Right, that's also one of the interesting important properties of coherent. It minimizes uncertainty of two conjugated variables, in this case momentum and coordinate. Fine, let us see. I wanted to discuss yet another thing which you will become useful. The thing is qualitative. Let me put it in qualitative phase a moment. To this end, let us believe in that visualization I presented for coherent state. The coherent state is a circle of the radius 1/2, 1/4, diameter is 1/2. And I compare its overlap with number states. In this way, I understand uncertainty of the photon number in this state. All right. It overlaps with many number states. Spread of the photon number in a coherent state. I could look at this visualization differently. I could think of a phase in this plane. And I see there is also a spread of the phase. Spread of the phase is proportional to radius. Radius is square root of n. So that's uncertainty of the phase. And we see that uncertainties in phase, a number of photons, they satisfy this relation. Heisenberg-like relation. Like momentum and coordinate, that will become important for us. But why don't we make a break at the moment, like 7 minutes break, perhaps it will suffice. That's me again. Let us see where we are now. We have found coherent state for a single oscillator, mathematical model, very nice. We look at the features of this. I would like to go a little bit more practical. First of all, I'd like to extend it to many modes, which are, for instance, in the electromagnetic field. Right, so how to do this? I could say that the big coherent state is a direct product of coherent states for each oscillator. For each oscillator, I would have a separate eigenvalue. And with all this, I can make use of a correspondence between lambda and average amplitude in each oscillator. That average amplitude I can see as a classical solution of Maxwell equations. So for any classical solution of Maxwell equations, I can find the corresponding coherent state. Coherent state minimizes uncertainties, or sometimes people say, oh, it's a best quantum approximation to a classical state of electromagnetic radiation. All right, that's natural because we have derived it as a kicking of single oscillator. If there are many oscillators, well, we just excite them differently, it will remain coherent state. So at least now we know how to describe classical solution of electromagnetic equations in a quantum way. Let's talk about lasers. And now I'm gonna go with nuances related to different definitions, different meaning of word coherent. So even in science, which physics, it's supposed to be rather accurate in language usage. There are different meanings of the same word, which might lead to confusions, but it also can be illuminating. First of all, let me state that laser light is highly, we will quantify what is high a little bit later, is highly coherent. And this is the definition of coherence used by opticians. It's optical coherence, which is the property of the irradiation to have certain phase. To this end, the light first has to be monochromatic to have certain wavelengths, and the phase of the slide should be kept well for a long time. That means optical coherence. Then we have computed Poisson distribution of number of photons in the laser. And it was a bit uneasy because we thought about laser in terms of number states. Now, look, we have a candidate state for the laser, which is called coherent state. It has the same distribution of the photons. It also corresponds to the fact that most lasers eventually have pretty much big classical field, much bigger than fluctuations of this field. So it has to be described by something like classical Maxwell equation. So coherent state is the best approximation. Okay. Can one say that a state of laser radiation is a coherent state? Now we are going to be a bit confused with different meanings of what coherent laser is coherent. It's not an argument for him to be in a coherent state. Right? If somebody makes money as a smith, it doesn't apply that his family name is Smith. But that's not real denial. The coherent state are useful to understand the actual state of the laser. At least they're much better description than a state with fixed photon number. Good. So let me give a short cartoon of what is going on. It's one thing is a penny laser, is what you can open systems, so there are photons going out of the laser. And there's some energy coming to the laser to give this to compensate for the photons which leave the laser. Opticians use quantum noise to describe this process. I would like first to talk about quantum noise. Is laser switched off? It is simpler. So I just try to introduce this concept for a mode which loses photons. So I write time-dependent equation for parameter lambda. Parameter lambda, parameter of coherent state, related to average number of photons in the laser, average amplitude of the oscillation. Right. And if I take into account that photons leave the laser, I understand that this amplitude should go down. Should obey certain exponential law. Quality factor of the laser is in this exponent. Right? So if I just look at this equation, it has a solution where lambda dies off exponentially. All right. But kind of argumentation is such that it cannot go to zero all the time. Because in quantum state, there's some uncertainty. And they put a noise to this equation, white noise, and reduce the magnitude of this noise in such a way that in average, the fluctuation of lambda in the state corresponds to the ground state. So lambda must be of this order. 1/4, I believe. Fluctuation of lambda. Right. If you look at it, at the system, what we have, it's like we have a parabolic potential which tries to put lambda to 0. And in addition to that, we have noise which sets up Brownian motion. If there is no parabolic potential, then lambda would do Brownian motion, diffuse from the center. And what is important for me is this diffusion coefficient. So it is proportional to quality factor of the laser. Very good. Let us switch the laser on and keep this noise at home, which sets off the diffusion. How about average lambda? Laser response, a certain number, a big number of photons in the laser. What does it mean in terms of our visualization? There is a central force which tries to set the state of the laser to a circle. So the competition between gain and loss, it sets the average number of photons in the laser, but not the phase of radiation which comes out. Good. So that blue circle is a coherent state which approximates the state of the laser. And without noise, it would just stay here. And we would have ideal coherent laser. But we just discovered that a loss of photons inevitably gives rise to noise, to the diffusion. So, as a matter of fact, which will happen in ideal laser is that the phase of the lasing would diffuse slowly, go back and forth, back and forth, back and forth, subject to the noise. And at some time, it will make the round, the change of the phase will be of the order of 2π, so it will make a round. And at this time scale, phase coherence of the laser will be lost. Fine, what you can learn of this? At smaller time scale, the laser can be nicely approximated as a single coherent state. At bigger time scales, well, eventually one cannot say about quantum coherent state. Quantum coherent state of the laser has changed many times because it has lost plenty of photons. Optical coherence has also gone at this time scale. So this is optical coherence time of the laser. So in fact, it's proportional to number of photons in the laser. Theoretical estimate for very big laser could be centuries. In practice, no laser would exhibit this limit There are fluctuations, for instance, of pressure in the laser or fluctuations in the processes which supply energy to the laser. Practical lasers have shorter coherence time. I guess best lasers now provide about a second of coherence time, which can have plenty of orders of magnitude in comparison with frequency, of course, like 16 orders of magnitude, but still they don't reach this ideal limit set by quantum noise. Your question?
Oh, you already answered.
Okay. Fine, that was about the lasers, open systems. Let me apply coherent states in a different setup when we don't have open systems, but rather let me talk about coherent state of particles rather than it is rather, it looks like a fancier topic. Well, for photons, we understand that coherent state is in fact classical state. But if you are thinking of particles at the number of electrons and quantum dots in a piece of solid, well, it's natural to assume that this state has fixed number of particles. From the other hand, we have known quite a lot in this course, and we understand that we have already found counterexamples. These counterexamples are ground states of superconductor and Bose condensate. And these states are characterized by a phase rather than number of particles. And the number of particles in these states is actually indefinite. So these quantum states are coherent states of the particles. Since these states, superconductors and superfluids can be really macroscopic, one also needs, would rather call this coherent state classical one. But it's a classical state of quantum thinking. So it's been yet another language exercise about classical and quantum. You see, sometimes these words have meaning, sometimes the meaning can become a little bit obscure. Right, I have a small example for you to understand coherent state of particles. It has also like some applications in modern technologies, those which are made in the building. I will ultimately discuss Cooper, what is called Cooper pair box. Let us see. Coherent state of particles. There is a little bit of paradox with the states. First of all, let us take infinite superconductor, infinite number of particles. And it has a certain phase. It has a certain phase. Superconducting phase. As to the number of these particles, it is not fixed, which is natural in a mouth and all numbers are infinite anyhow. But owing to this Heisenberg uncertainty relation, it would mean that fluctuation of number of particles will also diverge. Right here. It follows from this relation that number of particles and phase are something like momentum and coordinate for a single particle. Those are incompatible quantum variables subject to uncertainty relation, which means that the commutator of these two just, of the order of one. Canonically conjugated variables. Fine. So infinite certain fixed phase, infinite fluctuation of particles number. Let me envisage another situation. Let me just take perhaps big but finite piece of superconductor. Or the superfluid will also work. In that case, since this piece is isolated, we know for sure that it's in a state with fixed number of particles. That means that fluctuation of the phase is infinite. So we have two extremes, and it's quite uneasy because it is two different extremes which are supposed to be consigned somewhere, because we understand that sufficiently big island is the same as a bulk. To remove the confusion, let me talk about Cooper pair box. And the idea is to give energy find, energy cost for each variation of the phase, and the variation of number of particles, and see what happens with this island. Good. So, as I said, it's a superconducting island, which is connected to bulk superconductor. The connection is provided by a tunnel barrier between these two pieces of metal, which is called Josephson junction. I will define it as Josephson energy in a second. Right. That Josephson junction introduces a fine for deviation of the phase, for fluctuation of the phase in the island. There is also energy which gives a phi to fluctuations of charge. It is called charging energy, and it comes about electrostatic energy accumulated in a capacitor between the bulk and the island. Charging energy. Just if you put charge into this island, there will be electrostatic field around the island that will cause energy. Fine, good. There is experimental picture, and that's quite famous one. It is a Coulomb Cooper box, which has been used in a device called Cosmo. basis of processing here and there. Yeah. Perhaps somebody of you was interested in this branch of science. Not really, you're all that biologists. When I first looked at this picture, I had a difficulty to understand where is this island in the picture. Do you have the same difficulty?
Yeah, I think it would be the thin bar at the top.
You've got to choose at 10. Your next page of you really have a life understanding. So how do you know this?
I mean, I compared it to your description of the ball in the island. And so the island, I was looking for something relatively small compared to the ball.
All right, that's good intuition. Very good. Yeah. So the island is eventually this little thing. And the junctions, let me give it in a different color, are these overlaps. And this blue thing is kind of pretty well connected to brown thing. So they both make a bulk superconducting electrode for this device. Okay, that's how it looks like in a real scale. 5 micrometers the whole size. Good. Let us set a Hamiltonian for this. Hamiltonian consists of charging energy that can be changed a bit. Number of electrons can be changed by gate voltage. Not very important now. It's hello. Yep, you can hear me. Now I want to restore the screen. And I guess I'm fine again. Energy to be paid for charge fluctuations. And this Josephson energy, it has also minimum at phi naught. And near that, it can be expanded as something proportional to phi squared. So at least at small fluctuations, it will be proportional to fluctuation. So we kind of regularize, we have energy cost for each fluctuation. Well, with that, we can solve, we can set a Hamiltonian and Schrödinger equation either in phase space or in a different representation in terms of discrete charges accumulated in this manner. Good. So let me look at the solutions in two limits. How do I get to these two limits? Well, I have two parameters, dimension energy, charging energy, and Josephson energy. So the limits is if one energy is much bigger than another. Let's see, first of all, let us talk about well-defined charge. In that case, superconductivity it's not that important. Josephson energy is not that important. And the states of Cooper pair box are the states of certain charge. All right. If we change gate voltage, if we try to influence the charge over there, each state with a given charge would make a parabolic curve. Different states will give rise to fixed parabolas. So all these three parabolas are fixed by this charge. To get ground state, I have to connect lowermost pieces of the parabolas that is given in red. The next pieces that will be blue and green. So it will be respectively ground state and excited states of the system. It looks pretty boring, but there is a very interesting and simple quantum effect. In this situation, it sets up when I look at the crossings of the parabolas. In this case, two charging energies corresponding to two different charging states are equal, and since they kind of try to change the levels into opposite directions, small Josephson energy becomes important. And in fact, if you look at the crossings, you find that there is a repulsion between the states, between the levels at the crossing, and the states themselves become superpositions of two different points. So that's would be the response to the topic of our lecture. It's not the coherent state. It doesn't involve superposition of many discrete number states, only two, but well, it is also a superposition. It's also a way to make the superposition of two particle states using superconductivity. Right. In opposite limit, when charge is opposite limit, when Josephson energy is much bigger than the charging energy, the picture is more complicated, but we also coming back to situation which we are pretty familiar with. Let me sketch this energy as a function of phi first. As I said, it's cosine, it's minus sine. So eventually it sets a barrier of this shape. No charging energy. The phase will be well defined, corresponding to the minimum of this barrier. Let's bring some small charging energy. It will energize fluctuations of phase. So That's gonna be an oscillator near the bottom of this potential first ground state of this oscillator. The excited states, which are equidistant near the bottom of this potential. That's what we see here. Good. And that goes on and on, but there is a finite barrier height. It's not parabolic. Eh? At some stage, the levels will get above this potential, which means that perhaps it's a good approximation to forget about some energy. And at higher energies, one eventually sees crossed parabolas, which I showed you in previous slide. Because charge and energy will be dominating. Right, so let us talk about one state of the system in the state that's closer to oscillator. Let me quantify fluctuations in phase and in charge. It's all about fitting it with a ground state of oscillator. So it will be large in our case, and fluctuation of the phase will be small. The product of these two fluctuations is of the order of 1 by virtue of Heisenberg. Good. So this is a demonstration of 19 coherent state of particles in an actual device. These states are coherent in the sense that they are superpositions. They don't have to be coherent states in the narrow meaning as we have started by keeping an oscillation. However, even for a Cooper pair box, we can find such a correspondence. All right. That will work pretty well. We replace Josephson junction with an inductor, which is pretty reasonable thing to do if fluctuation of phase are small. And in this case, well, this Cooper pair box, in fact, represents coherent states of matter, coherent states with different number of particles in the island. From the other hand, it is nothing but coherent state of radiation in pretty narrow sense of this word. That's how particles and radiation again come together in the setup of, I could say, nano electronics, nano fabrication of superconductors. Good. Oh, I have plenty of time. Any questions, perhaps? Yes?
How are these two properties used? This coherent state of matter modeling and
They can be used for money raising, for writing grant proposals and providing money for your own research or research of your friend. In fact, we have concrete device, concrete physical situation, concrete model. What we put here are just word labels. And it's one of the messages of my lecture. These word labels can be explaining and explaining, but could be also confusing. Say I use the word coherent at least in 4 different meanings during the lecture. So it's better to keep concrete model, concrete Hamiltonian in mind, thinking about nice labels, which describes as Hamiltonian, describes as limits, but still remain on the ground of this Hamiltonian and not going to a known direction with this worldly. It can be confusing. Good? More questions? Let me just shortly go through all transparencies. Good, so I guess I made the plan. I started with general wisdom. I tried to sketch general superposition of photon states. Then I concentrated on really simple but clear problem. I picked an oscillator and wanted to figure out what is the resulting state. Right, it appears to be, after some reasoning, that it's eigenfunction of the annihilation operator, which is narrow definition of being coherent, like Mike Smith. Right. We look at it at different sides, describe different properties, visualized it. We understood that it's a best approximation to a classical wave, to a classical solution of mass derivation. Then we wanted to apply this rather abstract mathematical concept. Right. So that end we have to distort it slightly, yeah, because it's idealized model. It has to describe real physics. We need to fit it a little bit. Right, so we do what was our conclusion about the laser. Coherent state can be pretty good approximation for a state of the laser, but only on a short time scale. If you go along a time scale, we have diffusion of the phase in the laser. We have the loss of its optical coherence. Right, that's what you describe as decoherence. We also look at coherent states of particles as the superpositions of particle states. So that would be natural if you take superconductor or superfluid. There is a paradox between making islands and making bulks in such systems, which we have decided to analyze on the example of practical device, Cooper paired box, and we see different superpositions of states with different number of particles, and even has found correspondence with a coherent state in narrow sense, coherent state of radiation. That was the story of today. So thank you for your attention.
Yeah.